Given this function, f of x equals x squared minus 5 all over 3 minus x, where x is any real number but not 3. We've got a minimum at point A and a maximum at point B. So first one's labelled x coordinate alpha, second one beta. Find alpha and beta and the y coordinates that correspond with this. So these are stationary points, therefore we can differentiate. Let's find df by dx, or f dash x. So I can use the quotient rule. I've got u and v. U dash is going to equal 2x. V is just going to equal minus 1. So we get u dash v minus u v dash over v squared for the quotient rule. 2x times 3 minus x. Sorry, I've just realized a bit more space. Minus u, which is x squared minus 5 times minus 1. So it's actually going to become plus x squared minus 5. All over 3 minus x all squared. 6x minus 2x squared plus x squared minus 5. Which is going to be 6x minus x squared minus 5. And is going to equal 0 for stationary points. So the only way that this could ever equal 0 is if the top is equal to 0. The bottom, we can't divide by anything to make it equal to 0. So I'm going to move over here. It must be, therefore, that 6x minus x squared minus 5 is equal to 0. And I can rearrange that to make it x squared minus 6. It's always easier to make the x squared term positive. And we're going to factorize. So minus 5 and plus 1. X equals 1 or 5. So the 1 is going to refer to alpha, because that's smaller, and the 5 is going to be beta. And we want the y coordinates as well. So if x is equal to 1, then y is going to equal 1 minus 5 over 3 minus 1. That's minus 4 over 2, so minus 2. And therefore, a is going to be 1 minus 2. I'm also just going to make it really clear that this is alpha, because it did ask us specifically about that. And then if x is equal to 5, then y is going to equal 25 minus 5 over 3 minus 5. So that's 20 divided by minus 2 is going to be minus 10. So b is 5 minus 10. Now we're given two new functions, g of x. This actually means that x is mapping onto x plus p. Another way of writing it is that g of x is equal to x plus p. And h of x is the modulus function. We're then told that we've got a new equation where we're basically taking the previous function right from the start of the question and applying some transformations to it. And what this does is take us from this equation here to one that has a line of symmetry down the middle. It's about the y-axis. And then the minimum points are have the same y value essentially. And then we're asked to figure out what p and q must be. So let's say I started with f of x, my original graph. What we're actually doing then is I'm just going to say that it's this little line here just means I'm transforming it. So I'm going to be transforming it to f of g of x, which is actually going to equal f of x plus p. So this is a translation by minus p0, or p minus p units in the x direction. Okay, so we'll look at that in a minute. And then I'm taking this same thing, this f of g of x, and I'm adding q to it. That is actually a translation. This is outside the brackets, is a translation by 0q. You could put these together as a single vector, but I want to treat them differently, I think. And then when I apply h of all of that, sorry, f of x plus p plus q, I'm actually finding the modulus. So let me get rid of that and just put the modulus around it. So let's take a look at the original function. We had minimum and a maximum. We had one at 1 and one at 5. So we want to subtract from the values so that they're the same side as the y-axis. So we need to think, right, I've got 1 and 5. What number can I subtract to make them the same magnitude, but they're going to have opposite signs? So 1 and 5. Well, if I subtracted just 1, I'd get 0 and 4. If I subtracted 2, I'd get minus 1 and 3. If I subtract 3, I get minus 2 and 2. So that's going to be it. Subtract 3 from both alpha and beta to make them the same distance, which in this case is going to be 2, from the y-axis. Therefore, p is going to equal 3. That's what I'm trying to say here. Then let's take a look. So the modulus doesn't affect that, but let's take a look at the translation. But remember that we're actually going to take the modulus after. So that, sorry, the y translation. Okay, so they're both below the y-axis at the moment. I'm going to be adding something on, but now I want to essentially, I'm going to add them so that they are also the same distance from the x-axis, but one will be above and one will be below. And then when I take the modulus, they'll end up in the same place. Brilliant. So I've got minus 2 and minus 10. This time, let's say I added, okay, if I add 6, then I'm going to get 4 and minus 4. But actually, that's going to work out. We're going to add 6 to the y values. One will be above the axis, 4 above the axis. One will be below the x-axis by 4. And then when I take the modulus, which is what I'm doing with this the final h function, then I will get them in exactly the same place, which is what I'm trying to achieve here. And so q is going to equal 6. Just going to write a few more words on it. Sorry, not subtract, add 6 to both minus 2 and minus 10. These are the y values that go with alpha and beta to give 4 and minus 4. Taking the modulus, will then transform them both to being at 4. So I hope That makes sense. We've got original graph. We've translated in the x direction by -3 to make them the same distance from the y-axis, translated up or in the y direction by 6, which has made them the same distance from the x-axis, one above and one below, taking the modulus then has it, so they're going to be in line, which is what we want here. We're asked to work out the coordinates of D. So if we look at that, we had as B, we had 5 minus 10. So if we apply the transformation, then D is going to go, remember we are um, adding 3, sorry, we're translating 5 and minus 10. Sorry, I made a little mistake there. I was getting confused. Translating by -3 in the x direction, so that's going to give 2. And then by 6 in the y direction, but then taking the modulus, so that's going to give me 4. So D is going to be at 2, 4. I'm just going to write down C as well, just so I've got it, -2, 4. Okay, we're on to the last part. We're given a function, which is the same as our original function over all real numbers, except now x is less than or equal to alpha. So remember, alpha was this point here, and I've actually already forgotten what it was. It was 1. So x is going to be less than or equal to 1, and it was 1 minus 2. So x is less than or equal to this value, so we can basically get rid of all this part of the function. It's worth just thinking about what happens over here, I think. So does the function ever equal 0? Well, if x squared minus 5 over 3 minus x is equal to 0, then x squared minus 5 must equal 0, so x will be plus or minus the square root of 5. So the positive square root would refer to this bit here that I've ruled out, but the curve will come up like this and hit the axis at minus root 5. We're asked to find the inverse of the function. So I'm going to let y equal x squared minus 5 over 3 minus x, and we're going to make x the subject. So y, or 3y minus yx will equal x squared minus 5. The tricky bit about this is that we've got a quadratic in x. So x squared plus yx minus 3y minus 5 will equal 0. So to make x the subject, we're actually going to need to solve this quadratic in x. Like in it, we've got a y in there as well, so we'll be working in terms of y. We can use the quadratic formula. X is going to equal right, so here's b, a is 1, and this is c. So I could bring it together like this. For c, it's going to be the whole thing. So x, let's make a little bit more space. X will equal minus b, so minus y, plus or minus y squared, minus 4ac. So that will be 3y plus 5 times minus 1, so this ends up being a positive, all square rooted over 2. Now, remember originally, well, our domain was x is less than or equal to 1, so most of our x values are going to be negative. We can also take a look at the range, and it's worth doing this actually because the range is going to be range of m is going to be the same as the domain of the inverse. So I think let's do that at this point. And we can use the graph for that. So remember we had -2 as this minimum point, and then the curve carries on increasing. So we had it go to minus root 5, but it's actually going to increase as x tends to minus infinity. It's going to go to infinity, and therefore the range of m of x is going to be that it is greater or equal to -2, which means the domain of the inverse is going to be x is greater or equal to -2. And if we take a look at the range, which I think I'm going to write down as well, then it's going to be that it is less than or equal to 1. So for this to happen, I'm going to need to actually ignore the positive because I want it to stay negative um, on the whole. And if I do the plus, then I'm going to go the other way. It's going to correspond with this part of the curve. So you have to be really careful with that. And therefore, the inverse function, remember I now basically swap the x and the y's around, and then the y becomes my inverse. The inverse function is going to be minus x minus the square root of x squared plus 12x plus 20. Let me just do that bit again. All over 2. Before I move on, let me just, okay, I just want to sort of clarify this. What's just happened? We had m of x, we had the restricted domain to make it a one-to-one function. Actually, that's absolutely vital because as it stands, without, well, the original function wasn't. It would have been a many-to-one function that wouldn't have had an inverse. But with the restricted domain, it is one-to-one. And we wrote down the domain. Later on, actually wrote down the range as well, because that then gives us the domain of the inverse, even without finding the inverse. To get the inverse, we let y equal the function and we make x a subject, because that gives us the opposite mapping. It's just right at the end, we swap it all round, because whenever you have a function, you always use x as your input. So we dealt with it, we got a quadratic in x, which is a bit trickier than you normally get with inverses, but we can still follow through and find the inverse. We've got use a quadratic formula, get a plus or minus, but you have to think carefully because one of them would correspond with the inverse of this side of the function and the other with the part we're actually interested in. So I said, right, we know that we're interested, or x in general is going to be negative. It's not always negative for these values, but it is on the whole. So that's why we're going to have to use the negative rather than the positive. So I'm just going to write that down actually. Reject positive. Um, this is the wrong side. Want x to be less than or equal to 1 after all. I don't think I need to justify it any more than that. Multiplied out the quadratic and got it back in terms of x, and that gave us our inverse function. And finally, we're asked to find the value of t such that basically the function and its inverse are equal to one another. So I might actually try and do a very quick sketch of the inverse. It shouldn't be too bad because basically the mapping just swaps around. If 1 maps to -2, then -2 would map to 1, and it would sort of end up here. Minus root 5 mapped to 0, so 0 is now going to map to minus root 5. So I think it's going to look... Oh, and then, no, that was it, wasn't it? That was the... It's going to end up looking like that. Okay, and then what happens with an inverse and its original function is that they are reflections of one another in y equals x. And sorry, I really haven't drawn this to scale, I've just realized. Okay, just gonna have to trust me that that is y equals x here. So it's this point that I'm interested in. Now, what you do not want to do or go anywhere near is trying to set your inverse equal to your original function. That will be an absolute disaster. Instead, we note it, well, we use the fact that they cross each other at y equals x and set m of x, in fact, equal to y equals x, or x in this case. You could also do the inverse, but the inverse is looking much more complicated. So we've got x squared minus 5 over 3 minus x equal to x. When we solve this equation, it will give us where the original function and the inverse crosses. I'm sorry again about this not great diagram, but it was hard to fit it in on the left. So x squared minus 5 is going to equal 3x minus x squared, which means 2x squared minus 3x minus 5 is equal to 0. And let's see if this factorizes. Okay, if I put a 5 here and a 1, no, not a 5 there, that's not a good idea. A 5 here and a 1 here, then I'll get 5x and 2x. So if I make this one negative and this one positive, it will all check out. Of course, it's equal to 0. So x is going to equal 5 over 2 or minus 1. Now, remember, my inverse is only defined for x is less than or equal to 1. So the other one is where like the opposite inverse sort of crosses this part. So we can reject the 5 over 2. X less than or equal to 1, which means that minus 1 is our answer. That is where they're going to intersect. Well done. Nice question.